Okay. Okay, so study finds that the carapace length of an adult spider is normally distributed with a mean of 18.21 millimeters and standard deviation of 1.26. Let X denote carapace length for an adult spider. Does anybody know what that is? I mean, biology. Carapace? Is it like the body of it, or what is that?
It's like the entire body.
Okay. Including legs or not? I've never heard of that before. Okay, so we want to sketch the distribution of the variable x. So what is the variable x? What is that referring to? Yeah, so this is the x is the it's the real world thing that we're talking about. So in this case we're talking about carapace length. So x is going to be values of x. So give me an example of a value. So we're gonna get a spider and we're gonna measure its carapace length. And what would be an example of a value of x we might get? Someone said 20. Yeah. Or you might get 17. All right. You're not going to get 50, right? You're not going to get 50 for this. Can you take the headphone out?
Oh, I'm not sorry. It's not on.
Okay, that's okay. All right. You're not going to get 5, and you're not going to get 60, right? You're going to get values around 17, 18, 19, around in there for the measurement of this in millimeters. So we want a distribution of those numbers. So what about this first one? Is it this first one? No. The mean is what?
The mean is 18.21.
Yeah. So most of the carapace length are going to be around what? Around 18.21. And so we see it right here. The frequency, right? The height of the curve is the frequency. So at 18.21 millimeters, you have most of the spiders have that carapace length. So that's why the curve is the highest. Then you get out to 21 and 22, you have a few, down to 16, 15, 14, a few. But most of those spiders are going to have this carapace length of around 18, and that's what that curve is showing. Make sense?
I have a question.
Sure.
Say you had, I don't know, a crazy number, like 1 million spiders, and you measured all of them, and all of them fell within like 14 or 22, except for one.
Okay.
That was like 50.
Right.
Something like that. Because you had mentioned something that those lines go on forever; they never actually touch the axis.
Right.
So could that still happen?
So it's like possible, but super unlikely. Like even like 30. So 30 would be like possible, but really unlikely. So it's just like, think about the tallest man in the world. What is he, like 7.5 feet, 8 feet tall, or something like that, right? So it's possible, but really unlikely. So that's what we're talking about. So yeah, that's the idea that, the actual the standard normal curve, it's theoretical. That's why it goes infinitely out in either direction, because it's purely theoretical. It's like it's what's the word? I can't think of the word, but it's acknowledging the possibility of very large outliers. That's the idea of it going to infinity. Acknowledging the possibility of huge outliers. But because the curve is so close to 0, it's like the frequency is just like nil. Okay? Question, yeah?
Okay, so I know for this one,
Yeah.
either this one or something else similar to this one.
Okay.
But when you try it and get it wrong, it says it's only the standard deviation plus or minus 2 times the amount, or plus or minus 3.
Okay.
Ignore the first one, just because we didn't have space.
Let's see if that shows up on this one, because I kind of need to see the question. I'm not really sure, so I'll continue. So hopefully that question will show up on this one. So the standard diversion of x is z. So we can take any distribution, any normal distribution, and we can turn it into the standard distribution by what? By normalizing the mean to what value? The mean then becomes 0, and the standard deviation becomes 1. So we can take any distribution and change its mean to 0 and it's standard deviation to 1, and then it's like all distributions can be compared on that level playing field, right? Okay, so how do we do that? We take that's the formula that we've done, and it's x minus the mean over the standard deviation. So which one of those is that? That looks like B to me. Because 18.21 minus 18.21, that gives us our 0. And then if we're one standard deviation up here at 21, 21 minus 18.21 is going to be, or whatever one standard deviation is, divided by the standard deviation gives us 1. So this will take our whatever distribution we have by doing x minus mu over the standard deviation, takes any distribution and standardizes it to the standard normal distribution of the variable z. Okay, so what's the distribution of z? What is the mean of z? Always 0, right? It's always 0. And then what's the standard deviation of z? Always 1. So the z distribution always, forever, looks like that. So it says find the z-scores that correspond to the percentage of adult spiders that have a carapace of lengths between 16 and 17 millimeters. So we've got x values, and we're just going to transfer them to z values. That's what they're asking for. Okay, so when x is 16, what is z? When x is 16, what is z? Well, we got that from up here, right?
1.754 minus 1.754.
It's going to be negative because we're below the mean, right? So 16 minus 18.21. And tell me again, what you got?
Minus 1.754.
What is that? Negative 1.754 what? What does that number represent? Yeah, so then this particular spider lies negative 1.754 standard deviations below the mean. Okay, and then what about 17? Was it 16 to, what did I say? 17. So this is closer to the mean, so it's going to be less standard deviations down. So what is it? What is this one?
Minus 0.960.
So about 1 standard deviation below the mean. So for spiders have carapace lengths between 16 and 17, that transfers to a z-scores between negative 1.754 and negative 0.960. Okay, thank you.
Minus 1.75 and 0.96.
Negative.
Minus 0.96.
Okay, good job. Okay, so it just didn't have what you were asking about, Heather?
I don't know. It seemed weird to me, but like as soon as I actually figured out what they were trying to say, it was fine.
Okay. So I want to talk about now, so this is kind of leading into what we're doing next. So if we were to look at those x values, we would go back to our x. So we said it was C. Shoot, it's right in the way, so let's do this. Let's do this.
I guess like a better question is when
Yeah.
we're drawing distribution graphs, do you want all 3 standard deviation places, or do you just only want the second and third?
It's
Because they only have the second and third.
it doesn't matter. Yeah, you're right. They're showing 2 away and 3 away. So just there's not a right or wrong answer. It's like they don't have enough room to fit in one. You see what I'm saying? Like when they put it on there, it looks like there's not enough room to get one in there. But actually, no, I don't think those are, because if the standard deviation is 1.26, these aren't actually 2 and 3. This is just noting the scale, right? Because 1 above would be what, 19.47, and then 2 would be 20.73. So 2 is 20.73. It's not even 21. So they're just giving some kind of scale on there. They're not putting the actual intervals of whole numbers of standard deviations. So it's just the way they chose to do the scale. All right, so for 17 to 18, we come along here. So we're 17, or 16 to 17, right? So an x value of 16 is right there, and then x value of 17 maybe is right here. So last time we talked about what's the significance of this. Now we're going to look at this distribution curve, and we're going to say, here's x equals 16, here's x equals 17. And we talked about what? Area. What's the significance of that area right there? Marked off by x equals 16 millimeters and x equals 17 millimeters. What would be the significance? She said the relative frequency of getting between 16 and 17. Right. We said there's this link between area under the curve and relative frequency of that range of the variable. So this area equals percent of the data that falls in that range. Remember saying that? This is where we're going. This is really important. So now that's between 16 and 17. What if I came down to the standard normal curve in black? What did we say? So if I were to go from negative 1.754 to negative 0.960, so here, remember for x equals 16, that had a z-score of negative 1.754. So say right there. And then for x equals 17, it has a z-score of negative 0.96. What's identical?
The relative frequency.
Right. And so therefore, what's true about this area right here? So by doing the area between the z-scores that correspond to the values of the variable, that area will be exactly the same as the area on our standard, on the x, on the distribution of x. So the area between 16 and 17 on the x distribution will be exactly the same as the area between negative 1.754 and negative 0.960 on the z distribution. So if we knew what this area was, right here, if we had that area, it would tell us the percent of spiders that had the carapace length between 16 and 17, because it'd be the same area as on the distribution of x. So that's where we're going with this. That's why we standardize, because we're going to have a chart. We're going to have a table, a chart of that's going to give us areas on the standard normal distribution, right? For z-scores, it's going to give us areas relative to z-scores. So then we can use those areas then to make inferences about any distribution. So if we have that area on the standard normal curve right there, that black area, it would be the same as the area, the red area on the x distribution, and that would be the percent of the data that falls between 16 and 17 millimeters. Okay, so that's now we're bridging the gap to where we're transitioning to where we're going next. So does that make sense? Any questions on that? Yeah, please.
That's a standardized normal curve, but I was wondering, what if you had like, left or right skewed? Would it be the same?
So we're right, exactly. We're specifically talking about the normal distribution. So right now. So that's we are focused on the normal distribution. So if you have a right or left skewed, I mean, there is no standard left or right skew, right? Because you could have you could have a large right skew, you could have just a little bit of a right skew, you could have a moderate right skew. So there's no, but with with the normal curve, it's a bell shape, and most of the data is in the center, so that can be standardized. Does that?
Yeah.
Yeah. Yeah. But you could name 100 right skewed curves that would all be different. But the normal distribution is there's just one normal distribution. Yeah. Yeah. And that's what we're focused on now. We're focused on variables that are distributed normally, which means most of the data is in the middle, and we have an equal smaller amounts on either side. Okay. Questions on that? Are you good?
I think so.
Okay. So should we look at the written homework? So for the written homework, okay, so we have a normal distribution, 52 grams, standard deviation of 17.2 grams. Okay, so sketch the distribution of the variable x. Okay, so which curve are we going to use? The first one or the second one for x? Right, because what's the standard deviation? 17.2. That's a really large standard deviation, meaning that the weights of sea urchins are spread out, right? You've got lots of different possibilities. So if the mean is 52, then it's not out of the realm of possibility that you'd have a sea urchin that's like, what, 20 grams or 15 grams or 85 or 90 grams, right? They're not all sea urchins are close to 52 grams. This is very spread out, right? So you can see that here in this curve. So we want to denote what our mean is. So right here, what's our mean? 52. So normally when you okay, so then so one standard deviation above the mean would be
69.2.
69.2. Now I'm going to verify this. Hold on a second. Let's go for it. Okay. So in terms of where is one standard deviation above the mean? So do you see how the curve is like cupped downward and then it kind of flattens out and then it's curved upward? You see that? So at the place where it kind of flattens out, right there, I think is about one standard deviation. So it's a rule. It's kind of just a rule of thumb to know where to put this. Where should we put one standard deviation? Well, it's about at the place where it's flat. Can you recognize that? Can you see that there? Okay. So what will that be? What will how many grams will that be right there? This is one standard deviation above the mean. 69.2. We're just going to add 1. And now you've got a distance for one standard deviation, so you're going to go out that same distance again, maybe right here. And what will that? What is it? 86.4? 86.4. Same way going this way, where it about flattens out, is one standard deviation below the mean. Thank you. And tell me again.
17.6.
And do you remember what we said about how much of the data falls between 2 below and 2 above the mean? Do you remember what we said? About 95%, right? And so thinking about area, that makes sense, right? So if we thought about area, we would be talking about all the area under the curve from here to here, which would just leave about 5%. Or so it'd be like 2.5% over here of all the area, and 2.5% of over here of all the area. Okay, obtain the standardized version of x, which we call z. So z, that's going to be our formula. What's z going to be?
X minus 52 over 17.2.
Good. All right, and sketch the distribution of z. What's in the middle? 0. What's here? 1. And then about 2 there. If you wanted, you could do 3. But really, from -2 to 2, we said is a large majority of the data, 95%. But if we want, we could, keep your even scale, and you could find where 3 is, and -3. Okay, so if we wanted, so this is the scale based on standard deviations, but what would be more, and you don't have to do this, but what would be more kind of realistic is that your scale would be just like by tens, right? So where's 50? So 50 is like here. 60 is maybe here. 70 is here. 80 is here. This is what, 50, 40, 30, 20. So it would, do you see what I'm doing? So based on, so if you just started, you were just measuring, like we were going to do a dot plot. We had a bunch of sea urchins, so we're going to make a dot plot. Well, your dot plot wouldn't have a scale like this, right? It would have a scale like this, 20, 30, 40, 50, 60, 70, 80, and then you'd be stacking the dots according to that blue scale, okay? It's just that we knew that the mean and standard deviation, so that got us started with the black scale, okay? Does that make sense? Okay, so the percentage of adult, okay, so this is the whole deal. If we want to know the percentage of sea urchins between 50 and 60, so what are we saying? I'm saying from here to here. That area right there is going to get me the percentage of sea urchins between 50 and 60. And what's that? How am I going to get that? How am I going to get that area? It's going to be the same as what? Yeah, we're going to get the corresponding z-scores for 50 and 60. And what'd you get for that? Negative 0.12? Yeah, that sounds right. So right about here. So negative 0.12. And 60 is 0.47. Somebody else get that? Okay, so you're in. So why do we do that? Why do we find the z-scores for 50 and 60? Because this area right here, tell me. Right. The area between negative 0.12 and 0.47 on the standard normal curve will have the same area as the area between 50 and 60 on our distribution for the x variable. And if we could get this area, then we know what percentage of sea urchins are between 50 and 60 grams. So normal curve, standard normal curve between what? Negative 0.12 and 0.47, right? The percentage of adult sea urchins that weigh with weights above 40 grams is equal to the area under the standard normal curve that lies to the, so 40 grams is where? I'll do that in red. 40 grams is here. So we want percentage of sea urchins that are above 40. So what would we want? What would we want on our curve here that would tell us the percentage of sea urchins whose weights are above 40? What would we want? Yeah.
Everything to the right of where 40 is going.
What about everything to the right? What would you?
The area.
Yeah. So I'll do a big cross right. So the part C is if we could get that area right there, that red area, we would know the percentage of sea urchins that are greater than 40 grams. You see? And how are we going to get that area? That area is the same as what? So when x equals 40, we're going to find the corresponding z. What'd you get for that?
Minus 0.70.
0.70. What? Does that say it? Okay, great. And so I'll do that in red also. So that's here. So what are we going to look for on the standard normal curve to get this area and therefore the percentage of sea urchins greater than 40? What are we going to look for? The area to the right. So we want the area on the standard normal curve that lies to the right of negative 0.7, which is the z-score for 40. You see? Is this better now? Okay, questions on the written homework? Yes, please.
So we were supposed to draw all of the problems on each graph that we did too, or is that just to like explain what's going on? Like how when we went through E and you drew it in red on the graphs from
No.
A to C?
No, it's not required that you do that. But I'm helping us to move on to what we're doing next. But they didn't specify that. You would just find the z-scores and just note the z-scores. But this picture is, what I'm drawing is crucially important for the very next thing we're doing. Okay. Other questions? Okay, so we can just collect that at the end with sheets if we do sheets, so just hold on to that. All right, so now the question is, what is that area, right? So here's this, we got this area, so we're talking about these areas, but we've yet to find an area, right? We've yet to find one of these areas and actually say, oh, we've got a percent of the data, like we know what percent of the data. So that is a matter of having a table of standard distributions of areas. So let's talk about that. So let me get it out first. So if you go in handouts and tables, there's three that we're using. The second one here is the Z distribution table, the standard normal distribution table, Z-scores. And I intended to give you hard copies when I came in the door today, but I forgot. I apologize. So we'll make do, but you want to print this out because then it's going to be one of your best friends in the course for the rest of the course. Hopefully it will load. Got it. Is there a way to turn it on this view? No, there's not. So we'll have to find it this way. Table. Z distribution table. Okay, There it is. So the way the table works is the table always gives areas to the left. Okay? It always gives areas to the left. So this left half of the table, as you see up there, it shows you that given a z-score, it's the table. You're gonna start with a z-score, and the table is going to tell you how much area lies to the left of that z-score. And this side of the table is for z-scores that are negative, right? Z-scores that are less than 0. Okay? The right half of the table then is for z-scores that are positive, greater than 0. But notice the picture, it's still giving values of area that lie to the left of that z-score. Okay? So the tables always give an area to the left. So I'll keep that up. I'll keep that, and let's see if we can find some examples here. Okay, so here we go. So suppose we had a z-score of 1.23. We have some distribution. We find the z-score by taking x minus mu over the standard deviation, and we get a z of 1.23. Okay, and so the table can tell us what that area is. So we want the area to the left for z equals 1.23. So if I go to the table, so that is a positive value of z, so I'm going to look here on the right side. And so what you do is you start with your z-score here is the ones place and the tenths place, and then the rows across here are the hundredths place. So if you get 1.23, you're going to start with 1.2. See that? And then we want 1.23. You see? So right here is the area under the normal curve to the left of a z-score of 1.23. Does that make sense? So what does that tell us about what we were looking at over here? So we got for a z of 1.23, we got area of 0.8907, right? Did I remember that number correctly? Okay, what does that mean? So what does the number 0.8907 mean? Right, 89%, 89.07% of the data falls below 1.23 for a z-score. So this area is 0.8907, and that's the relative frequency of all the data below 1.23. Okay, so what if we needed the area to the right? What if I wanted this? I want the area to the right of a z-score of 0.76. How can I use the table to do that? She wants to the left and subtract from 1. Yeah, because the total relative frequency of everything is 1, right? The percentage of everything is 1. So the area beneath the standard normal curve is 1. And so if we could get that area, it's like the complement principle, right? It's the not principle. So we want everything that's not the area to the left of 0.76. That's our 1 minus. So we go back to the table. We're looking for 0.76. Again, that's a positive z. Okay, so that's a positive z. So I'm going to start over here and look at what? What am I going to look at? I'm just going to come here and look for 0.7 and then 0.6. You combine those two, so that would give me a z-score of 0.76, and that is, so what does that say? It says that 77.64% of the data lies below a z-score of 0.76. Therefore, how much of the data lies above 0.7764? 1 minus that, right? So all this over here is it 0.7764? Therefore, this is the area equals 1 minus 0.7764, which equals, one more time, 2236. So the percentage of the data that's greater than 0.76 for a z-score is 22.36% of the data. Okay? So finally, we got another situation. How about between? So how would we get an area, say, between a z-score of negative 0.68 and a z-score of 1.82? Can you imagine how you could use the table to get that area?
Could you take the z-scores
Uh-huh.
for to the left of the 0.68,
Uh-huh.
to the right of the 1.8? Wait, no. Never mind.
Okay. So we know we could get this area here, right? We could get this area here. That would come right from the table. And then if we go to z point 1.82, what would we get? We would get all of this.
Okay, and then subtract the area of the left, the negative 0.68 from.
Right. Yeah. Excellent. Yeah. So hopefully you're all seeing that. Should have done red. So let's do red over here. So the black would be the area that we'd get from the z-score of 1.82. That'd be the black. The red is the area we would get from a z-score of negative 0.68. What do we want? We want the area of just this part. Well, the only black, right? Only black. So let's do. So we're going to find. So z equals 1.82 gives us, and z equals negative 0.68. Let's go and do those. 1.82. Is that the first one? Okay, so for 1.82, in this column, I'm going to look for 1.8, and then in the 0.02. So that combines to a z-score of 1.82. Everybody see that? And we're going to get, what does it mean? 0.9656. What does it mean? Joey?
96% of the data falls to the left of 1.8.
Good. Yeah. So if your z-score is 1.82, then that value is greater than 96.56 of the data. Or yeah. We got that. And then we want to, what was the other one? Negative point. Okay, so we got, so where are we going to look? So we're going to start looking down this column. Where are we going to look? Negative points way down here at the bottom, negative 0.6. And then in which column are we going to look at? So the second from the end, because I'm not going to be able to see that 0.8. But we're going to look in this column right here for the 0.8, right? So negative 0.6. Is it this one right here? Okay, so we got 96.56 oops, and 0.2483. So for z equals 1.82, it's going to give us area of,
9656.
okay, tell me again.
Negative 0.283. 2483, sorry.
Is it negative? No, it's giving area. The z-score is negative, but it's giving us the area to the left. So areas are always positive. Areas are always positive because it's going to be always just how much area is to the left. So you'll always have a positive area. So this over here is about 24.8%. All that in there. And then starting at z.182 all the way to the left is 0.9656. So to get the area between, I'm going to subtract. Anybody got it?
0.7203.
7203. So what's the significance of that area being 0.7203? Somebody knew. Daisy, what's the significance of that area being 0.7203? 72.03%. What? What about 72.03%? What about it? Yeah, you can see. Right. Yeah. So it's the percent of the data that falls between a z-score of negative 0.68 and when your z-score is 1.82. The area is the same as the percent of the data or the relative frequency. Okay, so how about let's, for your sea urchin homework, let's actually find the percent of data between 50 and 60 and above 40, okay? So let's actually do that. You do it on the back or, and what I'll do is I'll put, you've got all the numbers on there. I'll put the chart up on the screen. So again, sorry that I don't have a chart for you to have at your desk there. That was the plan that didn't happen. Can you read it? So let's, 50 and 60, are those both greater than? No. Yeah, now we're actually getting the percentages. Let's do greater than or equal to 40 first. What was the z-score for 40? Negative 0.70?
0.70.
Yeah. No, we're going to do the second one first. So I want to find what I want is the percentage of sea urchins that have a mass greater than 40. Is that what it asks? Is that what it is? Percentage of sea urchins with a mass greater than 40. That's what we're after. So how would you do that? So we're going to put it all together now. How would you get the percentage of sea urchins with a mass greater than 40? So this is our. So here are the column headers that you can't see up above, okay? Everyone making progress. Did you get it?
So we're trying to find the 0.70 right now.
So if you want, we want the percentage of
So it
sea urchins
just
greater than 40.
So it would be the 0.2430.
So we want to be between 1560, right?
Yeah.
It's be 1.2 and 4.7. No, 4.7 is
Everything right of 40, which is the same as everything to the right of negative 0.70. And how are we going to get that? Because that's going to give you everything to the chart always gives you area to the left or relative frequency to the left. We need to the right, so the total sum of the area is 1. Complement of 1. Are we good on the 41?
You just take 1 minus 0.2420.
I'm just rounding the one number.
Yeah, that's the table.
Yeah.
Can't always.
Are we good on 40? You guys good? Okay, are we good on 40? Does that make sense? So if we go back to no.
Are you using?
So let's bring that back up again. Okay, so let's talk about that. So where was 40? How many standard deviations below was it?
Table first?
Negative 0.71.
3.70. Negative point.
So this was our, what was the mean again?
Negative 0.7.
No, the mean. The mean.
52.0.
And then one standard deviation below was?
34.8.
So here's our, we're interested in, right there is 40. Okay? We're interested in the number of sea urchins, or not number, but the frequency or the percentage of sea urchins with a weight above 40. So how is that seen in this graph? How is the percentage of sea urchins greater than 40 grams seen in this picture?
It's everything past that line.
When you say everything, you mean what?
The area.
Area, right? So this area is equivalent to the percentage of sea urchins greater than 40. How are we going to get, so if we want that area, that's the same as what area? So we found the z-score for 40 and we got Negative 0.72? Oh, sorry. And why do we want that? Why do we want the z-score for 40?
Find the percentage.
Everything to the, if we want all the area to the right of negative 0.7, how does it compare to all the area to the right of 40? Same area, right? So if we find the z-score and get the area in the standard normal curve, that will be the same as the area for the corresponding x value, 40, to the right of that. Okay? So this area that these areas are the same. See, we don't have a table for distributions with a mean of 42 and a standard deviation of 16, right? We don't have a table for that. We don't have a table for a mean of 52 and a standard deviation of whatever, 18 point something or 16 point something. So if we have a normal distribution, we can standardize it to the z distribution, and then use those areas because those areas are equivalent. And you guys found that area was what? So you found this area right here down here, which is?
It's 0.242.
I don't think that area is 0.242.
Sorry, it's 0.758.
75.8%.
What is 0.242?
That's the z-score.
Nope.
No, what am I talking about?
This is the area that the table gives you, right?
Sorry, I like.
That's okay.
Down.
You just no, you know it. You're just talking too fast. That's okay. You're just talking before you're thinking. You got it. I think you do. All right. Just think before you talk. All right. So no, it wasn't meant to be fast. Just slow down a little bit, and you got it. The table gives you the area to the left. And so you got that was the red is the 0.242. Therefore, the area to the right is the 0.758, 1 minus that, and therefore that's the same as this area, 0.758, which is the same as? No, so that's the whole point. So this area up here is 0.758, and why do we want that area? So what? It's an area. So what? Right, we just found out what percentage of sea urchins have a mass greater than 40. That's the significant thing. Area is just our vehicle, right? Area is kind of superficial. It's like, so what? Area, who cares, right? But it's our vehicle. Area is equivalent to percentage of data, right? That's what we're interested in. We wanted to know how many sea urchins, or what percent of each sea urchins would be greater than 40 grams. Okay, let's do the other one. So the other one was a between, right? Between 50 and 60. So we want to find we're interested in the percentage of sea urchins between 50 and 60.
Z-scores.
Negative what?
Negative 0.12.
Oh, these are in totally different spots on the table. So we'll do that first. We'll do the z-score for 50 first, okay?
Negative 0.2.
Say it, what is it again? Does this do, okay.
0.12.
So am I showing it right now?
Yeah, 0.1.
Everyone got it? Okay, write it down. So that's the first z-score, and what's the other one we need? 0.02. Am I showing that now? Okay, write that down. Is it showing or not?
Wait, no, not anymore. Wait, are we looking
Okay, so for 50,
50 would be minus
what was the z-score for 50?
negative 0.12.
0.12. Did we get that z-score?
Yes.
Or I mean, did we get the area? And then for 60,
It would be 0.47.
0.47
Yes.
was the z-score.
0.47 would be 6.8.
The z-score was 0.47?
Yes.
Cool. All right. So do we have our areas that we need?
Yes.
Okay, so let's go back to the, write those down. We go back to the picture here. $52 and $70. Work together. Go. Do it.
Done.
Good. Got it?
Okay, so we would just do. Wait, okay, but so the z square of 60 is, if that's like, yeah, but is that 60? 60 is the amount of, yeah, so this is, so 68.08% of COG
It's
where averages 60.
0.680 is your area for 60.
Or wait, so wait, less than 60. So this is the amount of COG they weigh less than 60.
Negative 0.12 and 0.47.
They weigh
Is it negative 0.12 and 0.47? Negative 0.12. Is that right? And 0.47.
We would have to subtract the 51 from 1. No, this is what you could do. You could subtract. No, really? Oh, yeah. I'm like trying to make this way more complicated than it really is. I was about to do something.
Okay.
You can
So
do it
tell
so
me.
many different ways. Oh, okay.
How about over here? Tell me your name again.
Jason.
Jason, how'd it go?
Good.
So tell me what we're doing. So we had z-scores of negative 0.12 and 0.47. Is that right?
Yes.
Those corresponded to sea urchin weights of 50 and 60. So what'd you do?
I found I just subtracted the z-scores for the 0.47 from the 0.12 since you had to find the area.
You're subtracting z-scores?
Oh, not the z-score, the percentages that we found.
Okay, cool. So what percentages did you get?
So it was 0.6808 subtract, and you subtract 0.4522.
So 0.6808, I'm guessing that was
Yeah,
That's
before
yeah.
0.47.
what I'm shading in blue. Everything to the left of 0.47 for a z-score. And then what?
And then you subtract the percentage of 0.12, and that's 0.4522.
So the red area is 0.4522. So all the blue area to the left of 0.47, we got that from the chart, 0.6808. All the red area to the left of the z-score of negative 0.12 is 0.4522. We're interested in
It lies between.
between. So he wants to subtract.
You subtract 0.4522.
Okay, and what'd you get?
22.86%.
So minus point, what is it, 22?
286.
Okay, and so what does 0.2286 have to do with this picture?
It represents the percentage of sea urchins that fall between 50 and 60.
Okay, awesome. So yeah. So and let's track it back. So what does that have to do with this picture? What does 0.2286 have to do with this picture right here?
It's the part that's just blue.
The area that's just blue. Good. That's the area that's just blue. And so then what does it have to do with this picture?
It's the exact same.
It's the same area between 50 and 60. And if it's the area between 50 and 60, our final conclusion is
22%.
22.9%
Yeah, yeah.
of the sea urchins have a mass between
Of
50 and
sea
60.
urchins weigh between 50 and 60.
right. 22.86% of sea urchins weigh between 50 and 60, because that's the same as this area, which we got from this area between the z-scores. Okay. Is this making sense? So now we're actually getting, not just talking about areas and frequencies, we're actually getting them. We get them from the table. So where's my... Okay. We've already done that. Okay, so here's another thing we have to be aware of. So this notation. So this is a little confusing. When you have this, z sub, and then a number. So meaning we're talking about when you see this, z sub alpha. What is this? This is the z-score that gives an area of 0.025 to the right. Under the curve. So this is starting with an area and trying to figure out what the z-score is, right? So this is an unknown z-score for a given area of 0.025, but it's not the area to the left, it's the area to the right. So how are we going to use the table to get that z-score? So now we're going to use the table to find a z-score, not find an area. So what are we going to do? We need to get the area to the left first, because that's what the table has to do with. So the area then is what?
Oh, wait, you would subtract that from 1.
Right. Good. So the area to the left just you can do it in your calculator. What is it? 975. So now that's an area, and we're trying to the left. We're trying to determine the z-score that corresponds to that area to the left. That's what z sub 0.025 is. The z-score has the area to the right, so our area to the left is 0.975. So we go back to the.
Oh, you can find that number on the z-score.
We're just working backwards now. Now we have the area. We have to figure out what the z-score is. Right, working backwards. Okay, here we go. So, are we going to look at the left side of the table or the right? Right. And we're looking for? Can you find it? Oh, I'll go to
Oh, I see it.
0.97. There it is. So the z-score is 1.9 something. What is it? 1.96. So we're in the column of the 0.06. There it is right there. So that z, so therefore z sub 0.025 equals 1.96. Okay, so what if we came up with an area, we're trying to find a z-score for some area, and say it was 0.8325. I'm looking for a z-score that has an area of 0.8325. What would I do? So can you find it? 0.8325. You see that it's between these two.
Yeah.
So therefore, the z-score I'm looking for will be what? Between those two z-scores, right? So it's going to be between whatever is 0.9. So go up here. 0.6 and 7. Right. So if my area is 0.8325, then my z-score is going to be we can estimate it to be, just go halfway between, because it's about 25 is about halfway between 15 and 40. So just pick the z-score about halfway between. So 0.965. Do you see? So sometimes you're going to get an area. It's not going to be exactly an area to 4 decimal places that you have. So it'll end up being between 2. So then your z-score is going to be between those two z-scores. Should make sense, right? It's going to be between those two. So this 0.96 and 0.97, then ours would be 0.965. Questions on that? So that's this Z alpha notation. Z alpha, remember, Z alpha notation is referring to a z-score that has an area to the right of whatever that subscript is. Okay, so let's do this one. So what is Z of 0.05? Z of 0.05. So what area are we going to be looking for? 0.995? Or 0.95, which is it? Just 0.95. 0.95. Am I showing it? 0.95. So we're doing 0 of 0.05. Z of 0.05. Means we're looking for an area of 0.95. And where is it? Let's see it. 0.8? I'm not seeing 0.82. Here. 0, 1, 2, 3. Is this 4 and 5? 0.04, 0.05. So it's between 1.64 and 1.65. In fact, exactly halfway between, right? This is exactly halfway between. So the Z is 1.645. Any questions on that?